All right, that seems like a quorum. Cool. Um, oh, never mind. Hey, you know. So everybody, my name is Max. I'm one of the fourth-year EM residents at the University of Michigan. I am going to introduce this talk, start with the first few definitions and slides, and we want to tell you a little bit about revolutionizing education in emergency medicine, unleashing AI's power. So let's go over our talk team here. So again, I'm Max.
I'm Mary Haas. Michelle Daniel from University of California, San Diego.
And I'm Carl Fitzgerald from San Diego.
We are very excited to get to talking to you today. We have no disclosures related to this talk. And I want to tell you a little bit about how we're going to kind of lay things out. So basically, the first thing we're going to do is just go over terminology. AI, the field, is basically a word salad. And so we're going to try and demystify a few of those things. And then we'll talk a little bit about AI in recruitment, a little bit about AI in assessment, and then how we personalize instruction through artificial intelligence. And the goal of this talk overall is really to get everyone sort of thinking about this elephant in the room, which is artificial intelligence is coming for the educational space. And we need to be prepared, and we need to start thinking about how we can use it to improve the curriculum for our learners, and maybe improve our quality of life as well. So, without further ado, let's talk a little bit about terminology. So this is the first thing that comes up when you Google AI word cloud. It's terrible. First of all, word clouds are terrible, and second of all, I don't know why the word chess is there like 13 times. And so this is just like a classic example of this sort of word salad, like hype fest that artificial intelligence has become, and artificial intelligence in medical education is not spared from that. So I want to use a little bit of my background, my expertise, which is in computer science, machine learning, to sort of introduce you guys to some terms and lay out a framework for how we can understand these things. A lot of what we're going to be drawing from here is like this specific study, which is a large scoping review of artificial intelligence in medical education. There are a few people in this room who are on the study, so shameless self-promotion. And basically the thing to take away from this is that AI in medical education is actually not new. The first articles were done in the 90s, and it's certainly been exploding in the last few years. But if you take a look at this article, you'll see just how rich of a landscape it's been, but how shallow of a landscape it's been. So let's discuss what actually constitutes AI. So AI, of course, stands for artificial intelligence. And the way this kind of works is that these terms act sort of like planetary orbits, where they're related to each other, they have common features, and sometimes they overlap a little bit. And so if you picture artificial intelligence as sort of like your sun, then you've got machine learning, data mining, and natural language processing all kind of orbiting around it, interacting with it sometimes, and like kind of taking their own specific facets of it. So let's talk a little bit about the big AI in the middle. So basically, the definition is relatively simple, but the implications are pretty profound. AI is a concept. It's an idea. It's the most general of all of these terms that defines any machine acting in an intelligent manner. And intelligence is obviously very hard to define, and no one can truly define it. But the most common way we do define it is by describing it as human-like, which is sort of our hubristic way of saying that we are intelligent. And so the goal is to have artificial intelligence allow machines to make decisions, learn from mistakes, generate insights, or understand language. So talking a little bit about machine learning, which you almost always see paired with artificial intelligence these days, machine learning is a discipline, it's an approach. The idea is developing mathematical algorithms and computational structures which produce computer programs that basically can make a decision given an input data. It's the most frequent way we achieve a semblance of artificial intelligence, and it is very old, like since the 70s. And so we'll talk a little bit more about machine learning in a little while when we discuss deep learning versus traditional machine learning. Natural language processing is any computational or mathematical approach, whether it's machine learning, artificial intelligence, or otherwise, that deals with natural human language, whether that's written, spoken, a combination of the two. That's natural language processing, and this is also quite an old field. Finally, data mining is something you hear thrown around quite a lot. Basically, what data mining does is borrows traditional statistical algorithms, and sometimes from artificial intelligence, sometimes from machine learning, to deal with known data sets. Its goal is to help us identify insights from known data sets rather than predict new decisions on unseen data. And so we're mining the data that we know is there for information. I want to zoom in for a second a little bit on machine learning because it has its own moons orbiting around it. And so traditional machine learning this is the one that's been around since the 70s. With this, you have a pool of data, and you as a human, usually an expert, examine your data and you extract what are called features from it. These features are often like mathematical transformations of the data itself. How many times is the word great said in an evaluation, for example? You extract those features and then you feed it typically to a mathematical formula, often borrowed directly from statistics, and you test how well does that mathematical formula discriminate between one or more groups. And this was really how we did things in machine learning up until the 2010s. It was around then that the deep learning revolution started to play a role. Deep learning is different. Deep learning uses what are called deep, which really is just more than 2 layers, neural networks, which are really just mathematical equations that sound fancy, to directly derive the features from the data itself. So the data in large volumes, and it takes very large volumes, is fed into these neural networks, and they develop their own internal representations of these features. They realize that the word good, when repeated or used frequently, is indicative of a good evaluation, for example. The downside of this is that it requires a lot of data, a lot of time, and a lot of money for initial training. The upside is that once you create one of these algorithms, you can use it in multiple domains and do what's called fine-tuning it for like much cheaper. And the truth is, the work has already sort of been done, and that's what we're building on when we do a lot of these educational interventions. So these different planets, these different orbits, can sort of recombine with each other, and as they do, they form different words, different products that we're familiar with today. And the biggest example I'm going to give is the one that's really been transforming the landscape recently, which is generative AI. So generative AI is artificial intelligence, humans behaving in a human-like, or machines behaving in a human-like intelligent way. Machine learning, because that's how you train or teach these algorithms to perform. Natural language processing, because to be human is to speak. And deep learning, because that is the type of architecture that these models are built upon. And so all these different concepts come together in one giant thing that ends up being large language models like ChatGPT, that's generative artificial intelligence. And so each of these terms can be independent of each other, but they are usually deployed together. And as they're deployed together, they form the different outputs that we're familiar with working in this landscape of medical education informatics and medical education artificial intelligence. So that's it for terminology. Let's talk a little bit about some applications.
Thanks, Max. So now what I'm going to do is highlight some really sentinel works that are related to AI's power to transform admissions and selection. So how many of you in the room are involved in some form of applicant screening, either for your medical school or your emergency medicine residency program? So a lot of you. Now, what is the bane of your existence related to applicant screening? Essays? What else?
Reading through med school grades, transcripts, and other nonsensical, like newsletters.
Yes. And how many applications do you typically confront each year? It's insane, right? I mean, so this past year at UCSD, we had over 9,200 applications to UC San Diego for 140 medical student spots, and we had over 900 residency applications for 12. That's nuts, and yet that's what we're asking you to do with your precious time each and every day. So Mark Triola and his powerhouse team at NYU conducted this study. AI screening of medical school applications, development and validation of a machine learning algorithm. And the aim was to explore whether or not machine learning could accurately perform initial screening of medical school applications and make recommendations to the admissions committee on who should be interviewed, further reviewed, or rejected. So the team used machine learning to build a predictive model on a retrospective data set that included applicants from 2013 to 2017. And the model was then prospectively validated in 2018, and its performance was compared to faculty screeners. Then in 2019, they actually conducted a randomized control trial where they basically compared the machine to faculty screening recommendations, and you were randomized to one group or the other. And so to create input features for model training, they extracted AMCAS application elements used by faculty screeners. And they took 85 different structured data elements. And it's important to note that in this study, they did not incorporate any unstructured data. So no text and personal statements or essays, no letters of reference, and no descriptions of the experiences. It's also important to note that in this study, they used demographics such as gender, underrepresented in medicine status, so race and ethnicity, and that can basically no longer be used in admissions decisions following the SCOTUS decision in 2023. So, continuous data elements were used for things like MCAT scores and GPA. Counts were used for like how many research articles or experiences did you have, how many work experience, leadership, and service activities. And then other data points like are you an in-state or an out-of-state resident were treated as a binary. So the accuracy of their model was really excellent, and the randomized control trial found no differences between machine and faculty screener recommendations to interview by either gender or URIM status, though faculty did recommend more learners of low socioeconomic status for interview than the machine. So the team at NYU conducted another landmark study, and this time this was led by Dr. Jesse Burke-Raffel, and this one was called Development and Validation of a Machine Learning-Based Decision Support Tool for Residency Applicant Screening and Review. And the aims of this study were really similar to the prior study, to develop and validate a machine learning model for decision support tool for residency applicant screening, basically just to decide who to offer interviews to. And in this study, a machine learning model was trained on a retrospective data set in a large IM residency program. And then it was compared to the performance of human reviewers on a held-out data set. And then in 2021, the machine learning model was prospectively piloted in what they called a restorative fashion. And what they meant by that is the model actually selected 20 individuals for interview that the faculty had screened out. And so then those individuals were offered interviews. And the idea was, could machine learning kind of identify these diamonds in the rough that would benefit from further review? And similar to the other study, to create the input features for model training, they extracted ARIS application elements used by faculty screeners. And these guys chose 61 structured data elements. And again, they did not incorporate any unstructured text. So no dean's letters, no letters of reference, no personal statements. And the machine learning model predicted residency interview offers with extremely high accuracy, even when they removed USMLE scores from the algorithm. So that was kind of an interesting finding. And the authors note that using machine learning restoratively may actually help mitigate some of our human biases in who we screen out. Now, this study, though, also used racial and ethnic demographics, and it was conducted before the 2023 SCOTUS decision on race and admissions. So then there was this neat little study by Reese and Ryder, and they used machine learning to predict who would be ranked and who would ultimately matriculate into their internal medicine residency program. And the model had really impressive accuracy for determining who would be ranked and a bit more modest accuracy at identifying who would matriculate. And that kind of makes sense when we think about this whole crazy match process. But what's really novel is that this could be used by programs to triage applicants based on the likelihood of an applicant ultimately being ranked at their institution and matriculating, which would allow scarce resources to be applied perhaps a bit more wisely. Now, a few groups have started to evaluate some of the application components that do contain unstructured text. So Kibble and I can't pronounce his last name, Plachaki, conducted a study comparing machine learning models and human raters when ranking medical student performance evaluations, which is colloquially called the Dean's Letter. So perhaps not surprising to some of you who read residency applications, this study found that all MSPEs have positive sentiments, and machine learning was unable to provide any reliable rank ordering of students based on the Dean's Letter. Surprised? No. So by comparison, faculty raters, though, were actually able to demonstrate consistent rankings using a rubric. So the machine couldn't do it, but the faculty could. Then, Seraph and colleagues, they used artificial intelligence to evaluate gender bias in letters of recommendation for general surgery residency candidates. And they used natural language processing and sentiment analysis for this purpose. And they highlighted that there are some potential biases that are currently built into our selection processes. And so they found more favorable language in general used for men and so let's see. So how many of you are familiar with the SAEM technology integration framework? Ever heard of this? Only a couple people. Okay. So SAEM describes 4 levels of technology's ability to enhance or transform our work. And it starts with substitution, where technology acts as a direct substitute with no functional change. And then augmentation, where technology acts as a direct substitute with some functional improvement. Modification, where tech allows for significant task redesign. And then redefinition, which is sort of the holy grail, where tech allows for previously inconceivable tasks. So I'm curious, out of the examples that I just talked to you about, where do you feel our current use of AI is related to admissions and selection? Which of these categories and why? Pre-substitution. Max.
I was going to say substitution.
Yeah, Max likes to say we're in the pre-contemplative phase still. So pre-substitution, anybody else? Anybody think the machine was capable of augmenting the human processes of processing like 9,000 applications pretty quickly? They could probably do it faster than the faculty did, from a time standpoint. But for the most part, we're kind of in the substitution augmentation phase. You were going to make another comment.
I would argue that it's not substituting yet. No one's proven that it's as effective. They just proved that they could also do it. Right?
Yes.
So you done a one-to-one analysis to see how it compares to the gold standard.
I think the randomized control trial did that to an extent, but I get your point. So, while AI clearly, I think, has the potential to augment human processes for admission and selection, there are a couple of downsides. And one of them is that it requires a fair amount of data cleanup that has to happen before you can even run AI algorithms. So that's where this whole issue of, man, once the thing is developed, then it can maybe really pare back that faculty time. But it does take a lot of time to develop these algorithms. But I do think that AI really has some impressive potential to manage large volumes of data efficiently and to at least do similar work to what we can. And I think it's important to highlight that admissions and selection processes today are actually wildly imperfect. And any models that we do build run the risk of replicating our current biases. But we also have some opportunities to think about that prospectively and build better systems. So one big challenge to conducting research using AI in admissions right now is what I mentioned a couple of times, and that's the impact of the recent SCOTUS decision on the use of race and ethnic demographics. And so we have a real opportunity in states like California because we have not been using race or ethnic demographics in our admissions processes for several decades. So I do think that we want to look to some states to replicate this work by NYU, but do it in a way that, can we show that this does not negatively impact our students who are underrepresented in medicine when we're not using those features. And then I think the last thing I want to talk about is future directions for this work. So using AI may help us further holistic review. It's really hard to have 9,000 applications and to really tell me you've got some faculty member that's holistically reviewing all of them. In general, what's happening is you're using some sort of cut points and then you're reviewing a much smaller subset. So at UC San Diego, what we're trying to do right now is we think we have an opportunity to leverage AI to identify features of learners and applications. At UC San Diego, we're attempting to repeat the studies, not only that NYU did, but we're actually starting to look at all of the unstructured data. So we are looking at all of the personal statements, the letters of reference, and trying to incorporate that into an even larger model. And then I think eventually what we're really hopeful to be able to do is link that admissions data to performance outcome data in our curriculum, in our residency programs. So I think that that's another sort of really interesting and exciting space to look at in the future. And then lastly, I think we have an opportunity to leverage AI to identify some features that might say, hey, this student's really going to help, they're going to excel in your specific school. It's that whole idea of trying to get to mission-aligned admissions and selection. And so that's all I've got on admissions and selection, and I'm going to turn over to Carl.
Awesome, great. My name's Carl. I'm from Stanford. I'm going to talk a little bit about some ideas conceptually about using AI for assessment. I'm going to focus primarily on the GME space, but I think a lot of what I'm going to talk about has some analogies to UME as well. I think one of the points that at least I'm trying to emphasize, and I think some of us are trying to emphasize in this talk, is the importance of us being involved in how we're using AI when we start to incorporate it into education, and really thinking about moving farther down on that SAMR framework to thinking about ways that we can enhance what we're doing as educators and do things that we really couldn't do before. It's really easy and alluring to think about automating a lot of the work that we already have to do. But doing that for assessment won't necessarily make our assessments any better. It'll just allow us to do the same work we're doing faster, but won't necessarily progress the field of assessment in medical education any farther. So I'd like you all to sort of keep this question in the back of your mind when you're working with AI as educators, and think, what can we do now as educators with AI that we really didn't have the ability to do before? So just keep that in the back of your mind. So what do we primarily use for assessment right now, at least at the clinical level? The majority is basic direct observation in the clinical environment. There's other assessments that occur in medical education, but the bulk of the information we gather, at least at the clinical time, is through direct observation in the environment, providing feedback, writing evaluations, and doing some sort of narrative assessment. And the question now becomes, how can we think about doing this form of assessment a little bit better with AI? How can we enhance our observational assessments through using AI? And the two main areas that have been described in the literature are better use of existing assessment data, so how do we better operationalize the data we have, and then enhancing assessment quality, so getting better data for us to make our decisions about. In terms of using data better, this is a study that Abbott et al. Did in 2021, and this was using NLP, natural language processing, to try to estimate clinical competency committee milestone ratings. They were pretty successful with the model they used, and this was really done before large language models had been in sort of common use and common practice. And there are some ongoing studies right now looking at using large language models to do this kind of work. but we haven't seen a lot of that data out there in the literature so far. But to think about, how could you do this with a large language model and what additional benefits you might get, I think we could envision using large language models to give us more robust context-aware interpretation of the data that we get in our narrative assessments. How many of you guys sit on a CCC for your residency? Okay, awesome. Yeah, so as somebody that sits on a CCC, I find it very challenging, and I know I'm not alone in this, to see trends across multiple different domains, multiple different assessments, across like our quarterly evaluations and even across years. So it becomes sort of like isolating each bucket of assessment data in sort of its own. And it's really challenging to see sort of those longitudinal trends and identify who needs additional assistance and where people are particularly heading. So LLMs could be deployed to help us better understand some of these trends in narrative data that we're gathering and allow us to make more impactful recommendations to our learners. And additionally, I think an exciting part about this is using LLMs to give learners more contextual information for the feedback they receive. So we could imagine using a model to help learners make better sense of narrative feedback that they get in real time and say, how does this piece of feedback fit into your recommendations from the CCC or additional pieces of feedback you've had in the past, and allow learners to sort of generate corrective actions in real time before we do our quarterly CCC meetings. In addition to more real-time feedback, LLMs could also be used to guide faculty in their observational assessments. We have pretty good guidelines published in the literature for what makes good narrative assessment. And this is a great study that was published earlier this year in Academic Medicine by Max and some colleagues. And they took this qual score, which is a score for evaluating narrative assessments that has some validity evidence, and then they use natural language processing to actually try to apply the score to assessments that had been done by faculty members. You can use this tool. You can go to this website here and you can put in an assessment and it'll give you a rating of the assessment in terms of a qual score. It'll provide some recommendations for how the assessment could potentially be improved. And right now this requires some extra steps, but we could imagine, if you have a way that faculty are submitting assessments, you could get some real-time feedback provided to faculty members. So the faculty member, who always writes "keep reading," they could get some real AI feedback that says that's not very helpful to provide to a learner. The other part about analyzing some of this data on large scale is we can start to examine whether there are some systemic biases in our assessment data on block, or, like I said, try to identify learners that potentially need more support earlier on. And there are a couple of papers that started looking at this, but as LLMs are just sort of coming online, we're going to hopefully see some more work in this space. The next part is about generating new data. So there's a lot of growing interest in generating analytic data for assessment, and this is using data from the electronic health record as well as existing sort of clinical data warehouses. We gather a lot of data about individuals in the clinical environment, and it's been really hard to operationalize that into any meaningful assessment. So a couple of efforts that have been done are these RSQMs, resident sensitive quality measures, and tracers, which stands for trainee attributable and automatable care evaluations in real time, which is a mouthful but an awesome acronym. There are some excellent examples of these being deployed. I think AI is going to make it a lot easier for these models to be generated. And then hopefully, as AI sort of becomes more democratically accessible to anybody with an internet connection, it'll make it easier to apply some of these models that have been developed in places that don't necessarily have data scientists or informaticians, places outside of NYU and University of Cincinnati where they have a lot of people working on this. So they can create the models, and then other institutions that have access to an internet connection can use AI to start operationalizing some of their data. I think one of the points I'm really excited about is the additional payoff of looking at some of these analytic forms of assessment is These assessments don't have to stop with trainees. There's a great need for more useful and actionable clinical feedback to practicing physicians, whether you're a faculty member or somebody working in the community, in order to facilitate lifelong learning. And a lot of the metrics that we currently have, things like door-to-doctor time or imaging utilization, they're not particularly actionable from an educational standpoint, and it's really difficult to look at some of these metrics and attribute a given human behavior because there are so many extraneous factors that go into one of those time frame things. So looking at applying some of these across the spectrum and then saying, you know, here's where faculty members are on some of these metrics, here's like a direction that we could point our learners towards and provide them some more real-time feedback about their clinical performance. The other point about gathering additional data is, I think, about expanding our observational capacity. So things like audio video recording, using wearable devices, using motion capture technology. The technologies that are required to capture that data aren't necessarily new, but AI allows us to make sense of a lot of that data. So incorporating objective analytical data with some of this new observational data will allow us to generate hopefully some new perspectives and reduce the burden of faculty being the only ones that provide observational data. I think hopefully if we get some more of these data points, it'll also allow us to make better sense of some of the observational data that humans are collecting. This is an image from a paper by Chris Hicks and Andrew Petrosniak up in Canada. And this wasn't based on learner assessment, but this is motion capture technology looking at people moving around the trauma bay. And they use some of this data to redesign the organization of the space. But you could imagine using similar motion capture technology to look at how trainees are moving about in a space or doing a particular procedure. Some of these have been done in the surgical specialties that you can see in the review paper. But there's a lot of potential here to operationalize some of this data that we weren't able to before. So what are some of the challenges? Like I alluded to and that we've sort of been discussing is this, I think we're going to see a lot of this tension between automation and augmentation. Like I said, it's really easy to think about how can I do what I'm doing right now but do it faster and easier with AI, but that's not necessarily going to get us better assessment data and help us guide our learners to becoming better physicians. So when we think about how we're going to operationalize AI, I really want to encourage you to think about how can we augment what we're already doing or come up with new forms of assessment that are going to be useful. I think in some ways AI is going to help with this because it's going to require us to reevaluate a lot of our forms of assessment that we currently have. You know, I think the impressive performance of large language models on standardized tests says less about the ability of AI and more about the limitations of multiple choice questions as an assessment modality. So as we see these models performing well on forms of assessment, we might say, hey, what are new forms of assessment that we're going to need to look at to evaluate humans that can't necessarily be easily replicable by a machine? And I think a corollary to that idea is thinking about as AI takes an increasing role in the clinical environment, it's going to force us to redefine what we value as human work. What are the skills that we really want our trainees to take away from a training program? And our assessments as educators have to be aligned with those behaviors. And this isn't necessarily a new concept. I mean, I think we went through this when information became rapidly available, like memorization sort of became de-emphasized. It was more about quality appraisal and where do you search for reliable information. And now we're going to be using AI tools and be forced to sort of reevaluate what are the skills that learners need to learn, whether it's critical evaluation of model outputs, how do you interface with an AI system well, or how do you really emphasize maintaining that human connection when there's more technology that gets into the clinical environment. And we have to think about our assessments and make sure they align with the things that we really value physicians doing. I'm going to pass it on to Mary.
Thank you, Carl. I'm excited now to switch gears a little bit and talk with you all about precision education. Raise your hand if you've heard of the concept of precision medicine. Yeah, I think most people in this room have heard of it. And it's helpful to think about that model because precision education is very similar except tailored to the learner instead of the patient. In precision medicine, we think about tailoring specific therapeutic and diagnostic approaches to individual patients. And in precision education, we think about tailoring specific learning interventions to individual learners. In the simplest form, we can define precision education as efficient delivery of the right educational intervention to the right learner at the right time. And what was once a pipe dream has suddenly become a lot more possible, given that AI is being increasingly utilized. And AI makes this more possible by systematically integrating large amounts of data and evaluating it to gain insights that can then be used to drive tailored educational interventions. Mark Triola out of NYU, one of the pioneers in this space, alongside some other authors, was able to develop this framework for how we might conceptualize precision medical education, and they labeled it P4. And in this framework, precision medical education must be proactive, meaning it must proactively collect data about trainees. It must be personalized, meaning it must generate timely insights based on that data. It must be participatory, meaning those insights must be utilized to generate specific learning interventions. And then it needs to be predictive, meaning it needs to look at meaningful outcomes, such as clinical outcomes, professional outcomes, and whole systems-wide outcomes. There are several different types of applications where AI allows for precision education, and they fall mainly into these 5 categories. There's adaptive learning systems, which include things like intelligent tutoring systems, learning analytics and data-driven insights, where there's dashboards that can kind of offer ways to synthesize large amounts of data and make them available for learners and teachers. Intelligent assessment and feedback, where natural language processing tools can be utilized to provide real-time feedback that can then help learners improve. And then virtual reality and simulated environments, which are particularly useful in surgical and procedural settings. And lastly, natural language processing and conversational interfaces, which might include things like virtual assistants or virtual chatbots, where learners can actually utilize them to ask questions and get personalized educational content delivered. I'm going to highlight, as the others have, just some interesting use cases for some of these. So in this study, it's an example of how they utilize natural language processing to provide personalized learning opportunities. In it, the authors actually developed a novel electronic advisor system that used natural language processing to identify 2 geriatric medicine competencies from medical student clinical notes in the electronic medical record. Those 2 competencies included whether or not they discussed advanced directives and whether or not they documented altered mental status. The system actually analyzed the real notes from the medical students for relevance to these competencies and then generated custom email alerts based on whether or not they were included to those students with embedded supplemental learning material customized to their notes. That's pretty cool. This was another example from Triola from NYU, where they took the EMR and they took medical students that were on clerkships, and they looked at what diagnoses were associated with the medical student charts. They then fed that into an AI system utilizing natural language processing and AI matching, and used that to generate custom emails to the medical students with related resources. You can see here on the right-hand part of the slide an example of one of those emails. It says, "Hi there, you recently wrote a note in Epic for a patient with a diagnosis of acute kidney injury." Unspecified. That part gets me. Below are some educational resources you might find useful, and you can see that it actually links to these digital platforms, and it pulls papers that are related to recent evidence in AKI that the student can then link to. So very, very cool. This paper provides an example of an intelligent tutoring system. So ITS, as they're abbreviated, are actual computer systems that offer automated tutoring environments to fit users' needs based on well-established cognitive concepts and algorithms. And they can provide personalized guidance and can adapt to each student's needs, which is really cool. And they've been shown to improve learning outcomes in many different applications. One major downside is that they're very difficult and costly to build, as you can imagine. This example, taken from pathology, utilized a natural language processing mechanism to give residents real-time feedback as they were writing diagnostic reports on pathology slides. And one of the models gave them feedback as they were typing, and the others waited until they submitted the report. But in both models, they saw 4-fold increase in the learning gains, and it actually didn't make a difference whether they got the feedback as they were typing or after they submitted the report. This is another really, really cool concept that a lot of medical schools are moving toward, particularly with support from national organizations like the American Medical Association and their Change MedEd Innovation Grants. And it's an example of learning analytics and data-driven insights. Vanderbilt is one of the medical schools that's really an exemplar for this. They have this incredible platform called VStar. Is anybody from Vanderbilt in this group? So VStar is a web-based application that supports their entire curriculum. It supports their curriculum development and implementation, their assessment, their feedback, and self-directed learning. So everything kind of feeds through this platform. And it contains a real-time dashboard display of all assessment for every student, organized by competency and by entrustable professional activity. And students and their coaches can monitor progress across time, and they can actually compare their individual progress to that of their cohorts. The school has actually created technology that will automatically capture student notes in the EMR and utilize NLP to rank each note for relevance to their core clinical curriculum. And then at regular intervals, the students systematically review their own data and make assessments, self-assessments about where they're at in terms of milestones. Their coaches do the same, and then they come together to reconcile that data. That reconciled data about each student's milestones are then given to the competency committees, which use it to determine if they're ready to advance to the next phase. And you could see how this has really amazing implications for time variable competency-based medical education, which is this movement toward considering maybe every EM residency doesn't have to be 3 or 4 years. Maybe some learners can progress at a faster rate, maybe other learners can progress at a slower rate. So you can see how just having that data could facilitate an approach like that. It also allows for aggregate assessment, so not only just looking at individual students, but when they were seeing patterns where a whole cohort of students were not meeting a competency, it allowed them to actually look and identify gaps in the curriculum that they needed to change for future iterations. And you could see how that would benefit not just individual students, but entire cohorts of learners. Virtual reality and simulated environments is another really exciting one, and I highlight this recent article from Academic Medicine about haptic science, which is the science of touch and gesture. And there was a landmark article in the 80s which actually categorized different types of movements and found that for pretty much all hands-on skills, they fall into 8 categories. And plugging those into AI models can actually allow you to give super detailed feedback on hands-on clinical skills, not just observing whether or not it was done, but did the student or the resident do it in the right order? Was the positioning of their hands on the patient appropriate? Was the force they applied appropriate? So you could see how you could get much more depth of information and feedback through this utilization. This is a really cool example. So looking at this theoretical use of haptic enhanced AI in a wrist reduction, you can see figure A shows this traditional observational approach of see one, do one, teach one. A medical student watches a wrist get reduced, they do one, and then they teach it to somebody else. Versus in this haptics enhanced learning experience, they're actually wearing gloves that can allow them to, after seeing one, feel one. The gloves can show them what expert force and movement feels like for the reduction. They then do one themselves, and then the gloves can actually measure their movements and give them feedback on whether or not they pulled hard enough or pulled in the right direction. So you can see how that would really kind of change the game with how we typically teach procedures. And so looking at some of these, you might kind of be asking yourself, where do some of these categories fall into? And in the interest of time, as you think about it on your own, I think, honestly, redefinition is one of the really exciting categories where some of this haptic science could get integrated. It would be rare without this kind of technology to be able to give that depth of feedback on somebody's movement and clinical skills. And I think that's one of the most exciting pieces. So obviously there's challenges. As I was putting together this talk, I saw a lot of theoretical things, a lot of pilots, but not a lot of actual published trials of utilization of this technology. And so it's hard to really know the impact on learning outcomes. They're also super time and resource intensive, often requiring significant IT infrastructure, like for that Vanderbilt dashboard, and not every institution is going to have those kind of resources. But in terms of actualizing them, collaboration and interdisciplinary research will be key, and I think what you're going to see next is really expansion and implementation of these existing pilots, which are super promising. And with that, I'll hand it back to Max.
Okay, so this ridiculous slide is just a reminder of what we've been trying to put across to you guys while we've been here, which is basically, I think we started this presentation with sort of like, look, there's some substitution happening and maybe some augmentation, but transformation is on the horizon, and we need to be prepared as a field. And so I think the thing that I want you guys to take away from this is that AI is probably now more accessible than it ever has been. The advent of large language models and a $20 a month subscription that gets you access to the most advanced neural network on the planet is reducing the barriers to implementing artificial intelligence in your own educational programs. And so we want to leave you guys with a little bit of a directional framework to sort of point you in the right direction as you work on your own projects implementing artificial intelligence in medical education. Basically, we're calling it the FASTETS framework. Basically, it talks about what form of AI you're using. So that means terminology, even though the terminology is tough. Your specific use case that you're applying AI to, whether it's like a virtual patient, a personalized learning platform, clinical guidance, your context, which is UME, GME, where you're applying it, what the actual educational focus of your intervention is, not just we did a cool thing for doing a cool thing. The technology that you specifically used, including any data sources you used if they're public, and any code you wrote if you needed to write any. And then the final one is the SAMR framework, which I'll put up just one more time, which is where we should be pushing ourselves. The era of substitution, we're implementing substitutes right now. We are rapidly going to be working towards implementing modification and redefinition type of interventions within the medical education landscape. So along those lines, I think we're sort of very interested to hear, what are you guys working on and what are your ideas along these lines? And of course, we're happy to answer any questions on any of these topics that we can answer. Thank you guys. Is anyone working on anything?
Okay, I have some questions.
Yes.
First of all, I wanted to say that those are great topics, and this is really good, and I appreciate you guys presenting. So, the first challenge is that, do you guys have institutional setups to assure that your AI queries remain HIPAA secure and local? And how did you convince your institution to do it, or did they do it on their own?
I can answer for the University of Michigan. We have a setup for this. I think if you went back 4 years, you wouldn't have seen even remotely the amount of infrastructure we have available for this. I think the advent of ChatGPT was kind of the writing on the wall that everybody needs to get their theoretical butt in gear. And so the University of Michigan has developed basically its own implementation of ChatGPT that uses OpenAI's models on our servers. That is HIPAA, FERPA, all the compliance. And so the infrastructure is there for us. If your institution doesn't support that, that becomes a much tougher thing, and it basically involves you sort of being the person who acts on the frontier at your institution, and usually that's not discouraged. Usually being like, hey, I want to implement AI. No one in this day and age is looking at you and saying like, oh, don't do that. AI is a fad. It's not. It's going to be around for a long time. So I don't know about you guys.
Yeah, I mean, same for us. Like, what is really key, I think, and this is where I think some schools will have this easier than others, is partnerships with like the CIO and the hospital, and making sure that we're all working in parallel. They're generating those, the HIPAA compliant environments. We're working with our informatics people to like build the back doors to Epic to get that assessment, data out. But it's really required people who deeply understand both the health system space and the educational space working together. Some of the barriers that we've encountered, so I was mentioning that admissions and selection study that we're now working on that's looking at the text data, which that data set is much larger than when you're not looking at the text data. And they were initially going to charge us $30,000 for the server space to actually implement that study. So some of these things can be quite costly, either requiring grants or other ways to support it. So, but I think the beauty of it is like once it's built, if you actually sat there and documented the hours that you were paying for of faculty time to do that application review, you're spending way more than $30,000. $30,000 starts to look like a drop
Yeah, the AI, for example, the qual score thing that Carl brought up was trained on, I think, a like $2,500 AI workstation that I built off a grant I got in medical school, and now it runs in the browser. So it doesn't even require any server power. It just runs on the user's computer if you need it to.
So some of the ones that run on your own computer, they take like a day and a half to give you an answer. And so I guess and so did the rest of you guys all have a supercomputer center at your university? All four of you?
I'm at UNM.
Oh, you're the same, okay.
He's at Stanford, so
Because
yes.
other places will like they get a business associates agreement with Microsoft, but then Microsoft still won't commit with Copilot to not keeping the results. Like they say they will like they're gonna throw away your query, but they'll save the results of your query.
I think the way I would look at it is this. There are going to be things that are low-hanging fruit for different institutions for different reasons. And so I would actually say the lower-hanging fruit is some of more the FERPA data, so the education data. So like, let's say you can start to use natural language processing to do evaluations of all of your clerkship evaluations, to summarize them, elucidate themes, and provide feedback to students. Like, there are things that aren't necessarily as challenging because they're not in that HIPAA compliant space, where AI can still help drive forward precision education. Yes, would we all appreciate the supercomputer center and that access? Absolutely. And I think that what we are going to see is digital inequities emerging, and already have emerged. I mean, when you look at what NYU, Vanderbilt, Michigan, some of these places are able to accomplish, most of us sit here and go, how are we going to do that? But I think then it's like, how can we borrow what has been done in other places? What is replicable at relatively low cost?
I think here's the difference too with like the big difference and the big democratization of this is like previously a lot of these ML models, like a lot of machine learning models, it's very expensive to train your own model, but you can do a lot with some of the foundational models that have already been trained. Like some of the OpenAI models, there are open source ones that you can run locally, and there are lots of ways to get around like the data privacy issues. Like I'm sure there are people wherever you are that have to work with, that are doing some data science in the medical record, or you can communicate with other people. And I think now, you know, a lot of this is done in the cloud, and buying cloud compute from Google or like Amazon Web Services, it's not expensive to run. You can buy GPU time. It's not expensive to do that. Not prohibitively expensive. It still costs something, but it's a lot cheaper than it used to be like 3 years ago.
Yes, sir.
Emergency medicine is special in a lot of ways, but I was thinking like for evaluating notes, evaluating like resident differentials and stuff, it's sometimes it depends on the timing of when the note is written. If it's too early in the visit, the vitals change, the results change. Like, do you have any strategies or approaches for testing everything about the visit before taking this?
I think that used to be a more difficult problem. It used to be that we would have to train separate models for like the quantitative data, like when the visit took place, you know, night shift, day shift, afternoon shift, when the note was started in relation to when the attending saw the, you know, so things like that. And then we'd have to combine them with other models that did natural language processing and some of the free-form data in sort of like what we call ensemble models, which are where like multiple models are making a decision and then there's one model taking those decisions and combining them together. The newer large language models do not have that problem. The one that ChatGPT just released, I don't know what that is, that ChatGPT released, basically is able to, in one go, like take like audio, text, and image data all together, and process it in one single model and produce an output. And sure, that's cutting edge today. They literally released it like 3 days ago, but in a year, everyone will be using it. Cool. We are about at time. Yeah. 4:54. So if you guys want to stick around, talk to us, we're happy to answer any questions. If not, we really appreciate you coming out, and we're obviously super excited about this stuff. Thank you very much.